Hello everyone, my name is Ali. I'm a postdoc at the Institute of Astrophysics of Paris, working with Celia Galli and the CMB group. And I would like to thank you for watching this video and thank the organizers for giving me the opportunity to present my work, which is in collaboration with Cyril Pitrou at the IAP. This is a topic that has been dead for a while, hence the resurrection part of it, which is to see whether we can generate magnetic fields in the early universe, known as magnetogenesis, from gravitational vector modes. So to put things in context, we have been observing astrophysical magnetic fields for a while in different systems, in low redshift galaxies, high redshift galaxies, even in the intergalactic voice and filaments. And they have been found to have an amplitude ranging from 1 microgauss down to 10 to the minus 3, 10 to the minus 10 microgauss, and extending in length from 10 kiloparsecs up to 10 megaparsecs. And the question is, where did these magnetic fields come from? How did they form? How did they end up having such large amplitudes and extending over large distances? Of course, several mechanisms have been proposed to explain this at the astrophysical level, starting from some seed original magnetic field. The process of forming these systems transforms the kinetic energy into magnetic energy, what is known as the dynamo effect. But this does not yet explain where this seed magnetic field comes from. Now, other mechanisms have been proposed to explain the presence of this seed magnetic field, but they have their own caveats. So the most likely scenario is that these magnetic fields originate from the primordial universe, what is called primordial magnetic fields. This is expected since the primordial universe was a plasma full of charged particles, so the presence of a PMF is kind of natural. Also, it has been shown in several works that the PMFs can help in easing the Hubble tension. So adding to another motivation why to study these PMFs. Now, under standard adiabatic assumptions of the initial conditions, it is very difficult to generate PMFs that are large enough to explain what we see astrophysically. So there's always an exotic component needed in these PMF mechanisms to explain what we see, either through some coupling of the inflaton field to the electromagnetic tensor, some symmetry breaking, magnetic monopause, things like that. And people have studied also the possibility of generating magnetic fields from gravitational vector modes, since these two quantities are basically vectors. So what we want to do here is to revisit this idea of generating magnetic fields from gravitational vector modes by introducing two new initial conditions and looking at the resultant spectra and comparing them to the data. Before delving into much details, let me give you a brief reminder of cosmological perturbation theory. In cosmology, we always divide quantities into a background and a perturbation. So for example, the metric can be written as the background metric, which is the FLRW1, and some perturbation. And the same thing for the matter quantities, where the stress energy tensor can be divided as some background plus some perturbation. These perturbations are classified depending on how they transform under general coordinate transformations, either scalars, vectors, or tensors. So for example, if something that is a vector, you can always write it as a derivative of a scalar that would contribute to scalar perturbations, and something that is innately a vector that cannot be written in this way. And the same thing for tensors with scalar, vector, and tensor contributions. So you might be more familiar with the Bardeen potentials of scalar perturbations that result in gravitational lensing, gravitational waves for the tensor perturbations, and there will be something equivalent for vector perturbations. On the matter side, there will be density and pressure perturbations, and also the most important one for us is the CMB, which has the temperature and polarization anisotropies. For these, when we are computing the correlation functions or the power spectra, each one of them will receive contributions from scalars, vectors, and tensor perturbations, except the B mode of the CMB that will receive contributions only from tensors and vectors. And this is important because when we are looking at measurements of primordial B modes, we have to make sure that we are taking into consideration both tensors and vectors. And I will go back to this point at the end of the talk. Now, under the decomposition theorem, we know that each type of perturbation evolves separately from one another. So the tensors don't speak to the vectors and they don't speak to the scalars. And the evolution equation for vector perturbations look like this. So the conformal time derivative of vector perturbations is proportional to some source that is known as the anisotropic stress. In the absence of this source, these vector perturbations will decay like 1 over a squared. And that was historically the reason why people were not interested in looking into these kind of perturbations. And so now the name of the game is to find appropriate initial conditions that can create anisotropic stresses and source these vector perturbations, allowing them to live long enough to have imprints on the CMB and generate magnetic fields. Now, since we want to compare to data, we need to compute power spectra. And so we take ensemble averages of these perturbations, and the same thing we do for scalar and tensor perturbations, basically. So we can write the power spectrum of vector perturbations to have an amplitude relative to scalar ones and some spectral index that describes the tilt or the way it changes with the scale. And from that, we can compute the power spectrum of the B-modes that are coming from these vector perturbations, and it would be eventually proportional to it. Now, on the electromagnetism side, the electromagnetic tensor is evolving in the early universe along with gravity, and a good balance between Thomson and Coulomb scattering results in a velocity difference between the photons and the baryons that can generate an electric field. That electric field can source the evolution of the magnetic fields that we need to explain astrophysical magnetic fields. So the initial conditions that I'm going to describe later share this basic mechanism. That is, some initial condition create large enough difference in velocities between the photons and the baryons to generate an electric field that will then source the magnetic field, which we call the PMF. And the same thing we did for the vector modes, we do for the magnetic field, we compute a power spectrum that is proportional to the power spectrum of vector perturbations, with the proportionality given by the transfer function that takes into consideration the evolution of the whole system. Once we have this power spectrum, we can compute a root mean square value, and the resultant value can be compared to measurements of the magnetic field. And traditionally, this RMS has been computed at 1 megaparsec. So the three main numbers that we want to look at is the amplitude of the vector perturbations, their spectral index, and the resultant RMS of the magnetic field at 1 megaparsec. Before introducing these details, the initial conditions, let me give you a reminder of an important property of vector modes that does not exist for the other perturbations. Since the evolution equation goes like this, we can see that under adiabatic initial conditions, where the quantity does not exist, the resultant solution for the vector perturbations becomes irregular as we go to earlier and earlier times, at stages that can result to the breaking of perturbation theory, and this could be considered as a challenge for general relativity. I'm making this statement in a provocative way. And so one might think, okay, I don't care about vector modes, let me just set their initial value to 0 and then everything is safe. But then I ask whether this would be considered some kind of fine-tuning, similar to the flatness problem that was considered as a fine-tuning and a motivation for the inflationary mechanism. But irrespective of this, in order to have regular solutions in the very early universe, we need to go beyond adiabatic initial conditions, and that's why we wanted to consider different initial conditions. So the first one is called the isocurvature one, that has been studied extensively in the literature, is that we assume that there is enough velocity difference between the photons and the neutrinos in the very early universe that can generate a anisotropic stress of neutrinos, which will then source the vector modes. This is, of course, difficult to justify, given that in the very early universe, things are highly tightly coupled, and so such a velocity difference is difficult to exist. Yet, we entertain this concept and see where it leads us. The second initial condition that we introduce for the first time is we call neutrino octopoles. So neutrinos follow a Boltzmann hierarchy with the evolution of the Elf multipole given in this form, and you can see here the contribution from the vector modes at the dipole L equals 1 level. Now, again, in the very early universe, everything is tightly coupled, so any multipole beyond the quadrupole is basically negligible. But we still assume that this is not the case, and for some reason, the neutrino octopole has a non-vanishing value at that time. This will be a source for the neutrino quadrupole, which is the anisotropic stress, that then sources the vector modes. This initial condition is even more difficult to justify compared to the previous one, but this is exactly why we are considering it, because we want to see to what extent we need to go in quote-unquote exotic initial conditions in order to generate large enough vector modes that can explain the magnetic fields. And the last initial condition we introduce is what we call sourced mode, which is basically assuming that there's some species, let's say dark radiation, that existed in the very early universe that directly sources the vector modes. These species are expected to exist in higher dimensional theories, and so they are naturally equipped with an anisotropic stress that will source the evolution of the vector perturbations. And the result is that none of these initial conditions basically produce big enough magnetic fields to explain what we see astrophysically. However, the best fit value of the cosmological parameters coming from these initial conditions to data does not entirely exclude the presence of vector modes. So when we fit the parameters of this model to data coming from Planck, SPT, and BAO, we find that for the isocurvature initial condition, the amplitude of the vector modes is 10 to the minus 3, that of scalars, and the resultant magnetic field is too small. But with this amplitude, we can see that the resultant BB spectrum from this initial condition is already in stark violation of data that is coming from SPTpol. This is why it was important to look at SPTpol, because if you look at a BICEP alone, this initial condition might have escaped the constraint, but SPTpol at intermediate scales comes and kills it. And of course, if you wanted to generate larger magnetic fields, then we would have to increase by hand, basically, the value of this amplitude, which will then make this even in more stark violation of the data. Of course, adding tensors on top of that, which is more natural, makes things even more difficult. Nevertheless, we need to do a proper data analysis for this initial condition and set an upper bound on its amplitude, and especially when combined with the presence of tensor perturbations. However, for octupole initial condition, doing the same exercise, we find that it can accommodate large amplitude of vector modes compared to scalars. However, the resultant magnitude of the magnetic field is still too small to explain what we see observationally. But with this amplitude, we can see that the resultant BB spectrum is showing similar fitting power to the one coming from Planck-based fit lambda CDM. Basically, this is just lensing, modes that have been lensed into BB. Of course, that doesn't mean that this is a detection of this initial condition. It's just a hint that there's something interesting happening. And so to make proper conclusions, we need to do proper data analysis, run MCMC, put upper limit on their amplitude along with tensors. And similar story happens for source mode, where when we first did this exercise, we set this additional dark species to source the vector perturbations at a redshift 10 to the 7, but then we found the magnitude of the magnetic field to be even smaller than an octupole case. And so we decreased the redshifts a little bit to allow for a further survival of the amplitude. And then we see that it can accommodate amplitudes larger than scalars, but the resultant amplitude of the magnetic field is too small to explain what we see astrophysically. Nevertheless, the fitting power of this initial condition is similar to the one that's coming from Planck-based fit lambda CDM. And so we need to do a proper data analysis for this initial condition as well, set upper limits when combining with tensors, and see what we get. And with this, I summarize and conclude this part of my work, which is to say that producing PMFs from a gravitational vector mode is highly unlikely, but it doesn't seem to be that data is excluding with absolute certainty the presence of vector modes. And so we need to constrain them along with tensor modes with the data that is currently available. And this is something that we already started doing with Planck, SPT, and ACT. And an important message that I would like to deliver is that irrespective of what is the mechanism that generates PMFs, if they have to have the amplitudes that are needed to explain the astrophysical magnetic fields and to solve the Hubble tension, those magnetic fields will back react on both tensor and vector modes, and that will change the resultant BB spectrum of the CMB. And so in the future, when we have primordial BB measurements from experiments, we need to be careful not to conclude directly from these measurements that they are coming purely from inflationary tensor modes. Before ending this video, I would like to switch gear and advertise another work that I did recently, that is to develop an emulator of Boltzmann codes, both class and camp, and that will revolutionize basically our cosmological inference. This work has been led by Sven Günther in Aachen, Cosmology Group, and I would be very interested to share this with you. And if you are interested, please check the paper and the GitHub of the code, and I'm looking forward to your questions and the discussions we're gonna have during the conference. Thank you very much.